Hello students, it's Professor Sansam, just finishing up some of the notes from today. As you'll recall, we're talking about periodic trends, and when talking about periodic trends, the things that we want to think about the most are Z effective, which is the effective nuclear charge, and N, or the principal quantum number, which tells us about the size of the orbitals for those electrons. We've talked about atomic radius and ionization energy and what the trends in those both look like. Now we're going to talk about a series of ionization energies. So we mentioned before the first ionization energy is to remove one electron from the atom. You can see that that's indicated here. Magnesium, it takes about 738 kilojoules to remove a single electron from a magnesium atom to make a magnesium plus ion. And when we remove the second electron, we start with our magnesium plus ion, we add additional energy, we get a magnesium 2 plus ion plus the electron. That's the second ionization energy. Every time we have to remove another electron, it's more difficult. So the second ionization energy for every element will always be greater than the first ionization energy, and likewise with the third and the fourth, etc. If we then look at the third ionization energy for magnesium, we see that instead of increasing, like this one sort of doubled, when we go to Mg 3+, so this third ionization energy, now all of a sudden it requires 7,000 kilojoules of energy. So a huge penalty when we're removing an electron from a filled shell, or the noble gas electron configuration is broken. So in nature, we find magnesium in the 2+ state, and in the 2+ state, magnesium is isoelectronic with neon. And so it has the noble gas configuration. When we try to break the noble gas configuration, we have this huge penalty. So in this case, the big jump in ionization energies in this series will be between the second and the third ionization energy. If we were looking at something different, like say potassium, we would expect the first ionization energy to be sort of normal, but then the second ionization energy would be very large because potassium plus has the noble gas electron configuration, or a filled energy shell. Go ahead and give yourself this iClicker quiz. Which one of these atoms or ions would have the largest ionization energy? Remember, you're looking for the thing where you would be breaking a noble gas configuration. These all have a noble gas configuration. They're isoelectronic here with argon. So now, which one would have the largest ionization energy? It's going to be the one that has the most protons, or our potassium ion here. So now, we need to talk about some anomalies in first ionization energies. Okay? And this is when there is an exception to the trend. So remember, the trend is always, as you go down a column in the periodic table, the ionization energy will get smaller because the electrons are in higher principal quantum numbers, N, and therefore farther from the nucleus. They feel less attraction to the nucleus. It's easier to remove them. As you go across a period from left to right, the ionization energies will always get larger. In general, this is the trend. They get larger because Z effective increases, and as Z effective increases, the force of attraction between the electron and the nucleus increases, and it makes it harder to remove an electron, so the ionization energy is higher. You can see this general trend if you look at this graph showing the atomic number and then the first ionization energy. As you go from hydrogen to helium, for example, you see that that increases as you're going across the period. And then as you drop back down to the next row in the periodic table, it goes down a lot. Okay, and this corresponds with that drop in Z effective going from the full energy level to the next energy level, where now the Z effective will be 1 again. So you'll see that lithium, sodium, potassium, rubidium here all have low ionization energies because of that. Now, the first thing that we're going to look at is aluminum and magnesium. So we'll see aluminum and magnesium here. This dot represents magnesium, this lower dot represents aluminum. So why is it the case that it requires less energy to remove the first electron from aluminum than from magnesium? And the reason here is because magnesium has a full S sublevel. So that first electron in aluminum is actually the first electron in a higher energy sublevel. So it's a little bit easier to remove because it's that very first electron in that higher energy level. So it's less stable and easier to remove. Remember, magnesium has the full sublevel. The S sublevel is full. We see a similar trend when we look over here at beryllium. Beryllium has the full S sublevel, and that's especially stable. And so it's a little bit easier to remove the electron from boron. We see the similar pattern here at the end of the transition metals. This represents zinc that has a full D sublevel, and then gallium, which has one electron in the P sublevel. So it's a little bit easier to remove that electron than it is for gallium. So having a full sublevel makes a difference here for zinc and then also for cadmium underneath it. Okay, second question, why is less energy required to remove an electron from oxygen than from nitrogen? So here we'll look at this purple circle and we'll see boron, carbon, nitrogen, oxygen, fluorine, and then neon. Notice nitrogen is higher than oxygen. So why does it require less energy to remove an electron from oxygen than from nitrogen? This again, because it's an exception, has to do with an electron configuration question. And in this case, nitrogen actually has a half-filled sublevel. A half-filled sublevel because it has 3 electrons in the P sublevel. And so because of those 3 electrons in the P sublevel, when you add another electron in oxygen, it's forced to pair, following Hund's rule. And when it pairs, there's some electron-electron repulsion from those 2 electrons being in the same orbital now. That makes it slightly less stable and makes it easier to remove an electron because of some of that electron-electron repulsion that you see. So having a half-filled sublevel also makes things a little bit more stable than they would be otherwise. So you see that pattern here with oxygen and nitrogen, and in the 2 periods below it, when you get down to antimony, we stop seeing that trend. And so this is a smaller trend, which sort of makes sense because it's a half-filled sublevel instead of the full sublevel. And it's because of this electron-electron repulsion. Something similar happens when you get the half-filled sublevel in the transition metals, which is why we talk about chromium being an exception to the rule for writing the electron configuration, because having that D5 configuration is particularly stable. And the same thing when we talk about copper having a D10 configuration, which is an exception to the normal rules for electron configurations. So again, when we're talking about periodic trends, the periodic trends, if they're following the trend, the explanations are based on Z effective and N. It's only when they're not following the trend, when you have an anomaly or an exception to the rule, that you're going to invoke some explanation based on electron configurations. Okay, the next trend that we need to talk about is electron affinity. Electron affinity is when an atom gains an electron to become a negatively charged ion. Okay, it gains an electron to become a negatively charged ion. And in general, this releases energy. It's exothermic. And so the value of the electron affinity is negative. So we usually talk about this in terms of magnitude or absolute value. Meaning the more negative it is, we might say that it's higher or it's more favorable. This doesn't work all the time because some elements will have positive electron affinities. In other words, it requires energy to add an electron to that element. You can imagine situations where that might happen. So let's look at the trends in electron affinity here in the first column of the periodic table. What we see is as we go down a column on the periodic table, we see that it becomes smaller or less favorable or less negative. And as we go across a period, for example, it's going to be hard because there's exceptions here. But in general, as we go across a period, they get larger. They become more negative. And so that means it's more favorable for it to gain an electron. Notice, if we look at nitrogen, for example, we have this trend that they're increasing, except nitrogen is actually positive. It's not favorable. And that's because, again, it's an exception to the rule. So we're going to invoke an explanation based on the electron configuration. Nitrogen has the half-filled p sublevel. And that means that when we add an extra electron to it, we're going to have an electron-electron repulsion in that first orbital where we're adding the electron. And this makes it unfavorable to add an electron. It has a positive electron affinity. You'll also see that, as we might expect, all the noble gases will have positive electron affinities because you'd have to add an electron now into the next principal energy level, which is a big jump from whichever energy level you're in. We also see if we have a filled sublevel here, so at the S sublevel that's filled, if we were adding an electron, it would now have to go into a higher sublevel, and so these are positive or very small negative numbers. Okay. So now let's talk about the explanations here. As we go across a period on the periodic table, they become larger or more negative or more exothermic or more favorable. And that happens because as we go across a row on the periodic table, the Z effective is increasing. Therefore, there's a stronger force of attraction for an additional electron that's added on, which means that it's going to be more favorable. And as we go down a column on the periodic table, it's getting smaller or less negative or less favorable because that electron that we're adding is going into an N, a principal quantum number N that's very large and farther away from the nucleus. So the energy release that you get from that addition is smaller compared to where the electron can go somewhere closer to the nucleus. So we have an iClicker quiz here. Which of these has the most negative electron affinity, or the highest, we might say, or most favorable electron affinity? Hydrogen, helium, fluorine, or neon? You might begin by eliminating the noble gases. We know that they're going to have positive electron affinities because we have to add an electron into the next highest energy level. So we're down to hydrogen and fluorine. It turns out that fluorine is going to be the winner here for the most negative electron affinity. And if we look back at our chart from before, we'll see it's something like negative 300 kilojoules per mole, where hydrogen is a lower number. This follows the trend for electron affinity increasing from left to right across the periodic table. If we look now at metals versus nonmetals, we can see that metals have low ionization energies and small or even positive electron affinities, and those tend to form cations, meaning they lose electrons. Nonmetals, on the other hand, on the right side of the periodic table, have large ionization energies, meaning it's hard to remove electrons, and large electron affinities, which means that it's more favorable to add electrons, and so those tend to form anions. Okay, the last trend we're going to talk about today is electronegativity. And this is one that's really important for you to understand probably the most important one that we're going to talk about. And that's because we're going to continue to use this as we are moving forward in the course, and you will continue to use this as you're moving forward in organic chemistry and biochemistry. It's sort of a nice way of thinking about these things because electronegativity combines ionization energy and electron affinity. Now, there's different ways to calculate it. Your textbook calculates it in a particular way. If you look at a different source, the numbers might be slightly different. But in general, we'll see that electronegativity increases in the same way that ionization energy and electron affinity increase as you go to the right across a row because of Z effective and as you go up because of N. So the highest electronegativity will be something in the top right corner. It turns out that it's fluorine, and we don't really talk about noble gases having electronegativities because this is defined as how tightly the atom attracts an electron in a bond. And the noble gases in general don't make bonds, and so we can't really talk about that in a meaningful way. So again, electronegativity, like ionization energy and electron affinity, will increase as you go up and to the right based on Z effective and N. And that's the periodic trend. The last thing I would have you do is summarize for yourself each of these trends that we've talked about today. Why do trends exist? You should invoke Z effective and N to explain those things. Across a period and down a group, what are the trends and why? For each of these 5 periodic trends that we talked about today. Thanks for listening. I hope this was helpful, and good luck on your exam.